So I'm going to go back to my account here and then look at live streams. So that's 2 days ago. And this one should be streaming.
Hey, see, you're live.
But are you guys seeing it? You know, because this is from 2 days ago. So I'm asking whether the current, the current one is getting streamed or not. Because I just, because it is? Okay, thank you. This is great because I don't even need to start up the browser to get the streaming to work. Because I just need a token, get the URL, and then the software OBS, which stands for Open Broadcast, System, will start streaming to YouTube. Cool.
I didn't do it like this from now on. This would be a great way to know if you're always recording.
Always what?
So if you do this from now on, this would be a great way to always know if you're recording. Like you
Yes.
don't have to have the class ask hey, are you recording?
Yep. So this way, I can do the recording, and the best part of this is you don't have to rely on me to upload the video in order for it to go online, because it is only having a 2-minute lag behind. So if an asteroid is to hit this classroom, we'll only lose 2 minutes of the lecture. Not that anyone here would really care in that case. Yep, so this is really cool. I like it. Okay. We are watching the actual, this is not the live stream of today. This is actually on the other day. Because I haven't signed it yet, so you cannot see the, well, maybe you can. Let me see whether you can see the streaming. How do you get to the streaming?
Just click on your channel name, and then it'll show up. Click on the and then there's the live stream.
Okay, cool. So just click this. Oh yeah, you're right. So this is actually live. Very good. Cool. But you can see there's a lag. There's a lag involved here, and it's even talking too. So that's cool. It's like a time loop. Yep. Recursion. This is recursion. The kind of stuff that you guys like. So now you guys understand what recursion really is. It's just like that. All right. So how was the program that was due today? That one should not be too bad. Yeah.
My question,
Yeah. Question?
On the assignment, you said you used the input from the previous assignment.
Yeah.
So I wasn't sure if it was supposed to be reading in the file that was outputted from the previous assignment.
No, you have to do it through standard in and standard out. So you have to.
CN, but.
So you use CIN, and then on the command line you use redirect.
So then, okay.
You can also use Notepad to look at the file and then hand type it one line at a time. I'm just kidding you, but you can. Yes, you can have your siblings or your kids to do that as a form of punishment. All right, so we'll go back to where we left off last time. So we are still in discrete probability, but we are pretty much done. Okay, so we have already talked about outcomes, events, possibilities, and probabilities. Okay, we talked about that. We talked about combinations versus permutation. We talked about with or without replacement, how an experiment is a sequence of trials. Okay, and then the subsequent trials can be without replacement, so you have fewer and fewer choices, and that's how we got the permutations. Frequencies and probabilities is really just a very short piece to basically say how do we relate frequency to probability. So frequency is, can be maintained by observing, and then using the frequency observed, you can then, basically say, okay, I think the probability of that happening is da 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 da. Okay. So are there any questions about what we have talked about so far? Not yet. Okay. So what we'll do today is we are moving on to the next one, which is discrete probability distribution. So this one is slightly different, okay, because we are not really just looking at, okay, what are the chances that you can win the jackpot of lotto, okay? So this time we are talking about a distribution, which is kind of more of a coin flipping kind of thing, okay? So let's say somebody is to flip a coin like 10 times. What is the probability that you end up with 5 heads and 5 tails? Order not being important. So how do you get exactly 5 heads and 5 tails when somebody flips a coin 10 times? Okay. So it can be head, tail, all interleaved. Can be 5 heads and 5 tails. Can be in any permutation. All I really care is 5 heads and 5 tails. So how do you come up with that probability? So that's basically what we'll be getting to. But before we get there, we'll talk about a few things that are required, because this part here is coming from the curriculum of this class. And that curriculum is written because of the template based on CID or California ID. It's basically a standard template that is agreed on by all the UCs, CSUs, and community colleges. So this way, when you graduate having taken this class, the universities understand that, okay, all of these particular topics. So that's why if it's on that template, I have to talk about it, because you'll be expected to know this stuff. Is that okay? All right. So we'll start with Pascal's identity, and then we'll go to the binomial theorem. And in the discussion of these things, we'll also talk about proof techniques, because the proof of the binomial theorem makes use of proof by induction, okay? But in this case, it's not trivial, but it's not really difficult either. So we'll go ahead and start with Pascal's identity. The first link is just a link to Wikipedia, or not Wikipedia, but somebody else's page. Okay, so they have their own way of explaining Pascal's identity. You can read that part if you want to. The second one is my own note. So this is actually my own writing. So we'll go ahead and start with this. Pascal's identity is basically the second thing. Let me just zoom in because there we go. So this makes it a lot easier to read from your perspective. So Pascal's identity is basically saying for k in 1 all the way to n minus 1, this equality holds true. Okay, and and an n only has to be a number starting with 2. Okay, but that's really a very awkward way of looking at Pascal's triangle. Does anyone know what is Pascal's triangle? Okay, you guys all know about Pascal's triangle. So let's go ahead and just double check on that. Okay, so let's see whether we know what is Pascal's triangle and what are the numbers that we are dealing with in a Pascal's triangle. Because it's a triangle, I'm going to start with 1 here. What's going to be on the next row? 1 and 1, right? And then we have 1, 2, 1. 1, 2, 1. And then what do we have next? 1, 3, 3, 1. But how do we get these numbers? So that's the next question. Sum of the two numbers above it. Okay, very good. So you can kind of imagine there's a whole bunch of zeros, elsewhere. So this way, when I move on to the next row, this one is really the sum of this row of this one, and also a 0 that we don't see. Is that okay? So you can kind of imagine that it's a sea, or it's a space filled with zeros, and every single time you want to get the value of a particular number, it is the sum of the two numbers on top of it. Okay, so even though 1 is on the edge, it is still the sum of 0 and 1. So in that case, this will be 4, this will be 6, this will be 4 again, and this will be 1. And we'll just do one more row. 1, 5, and then we have 10 in this case, 10 again, 5 again, oops, 5, and then the 1. So this is known as Pascal's Triangle. Pascal's identity has to do with Pascal's Triangle, okay? Is that surprising to you, that Pascal's identity has something to do with Pascal's Triangle? Well, maybe, because sometimes the same name doesn't imply anything. Because the Pascal programming language has nothing to do with any one of theirs, right? So, all right. So then when you look at, I'll keep this one on one side, maybe down here. That's a good place. So let's pick just one row, okay? We'll pick one row to look at it. And let's pick this row here, okay? So when we pick on this row, we are basically saying, so for this row, n is 3, okay? For this row, n is 3, and then k is going from 1 to, if n is 3, k goes from 1 to 2. And so, it is basically saying, how do we come up with the value of the next row? Because this n plus 1 is referring to the next row, and then this k is basically the first one. So everything in the first column, this entire diagonal line, is basically k being 0. So this is actually wrong because k goes from 0 to n minus 1. I think it goes from 0 to n. Okay, let me think about this a little bit. This is still true. It just doesn't take the edges into consideration. That's all. Okay. So we'll take this row into consideration. It is 3. What is 3 choose 1? K being 1. Okay. 3 choose 1. How do you expand this thing? Yep.
It's just 3 factorial.
It's just 3, right?
I can't 3 factorial over 2 factorial, which is 3.
Yep. Because how many people still remember what is a combination? How do you express combination in factorial? Okay, so we'll say we'll make a more general case. N choose k. So when we say n choose k, how do I express this as a whole bunch of factorials with a division? It's n factorial divided by k factorial times n minus k factorial. That's the definition of combination, okay? So when n is 3 and k is 1, what do we get? You get 3 factorial on the top, and then down below you have 1 factorial times 2 factorial, right? 1 factorial is 1, so it's not really that important. 3 factorial divided by 2 factorial is 3. Is that okay? So that accounts for this number 3 here. What about this one here? This is the one next to it. Let's see. No, this would be 3 choose 1. This is 3 choose 2. This is 3 choose 1. That is 3 choose 2. Depends on how we pick the k. So we pick k to be 2. What is n choose 2? I mean 3 choose 2. What is that going to be? It's the same number because you have 3 factorial on top divided by 2 factorial times 1 factorial. So 3 choose 2 and 3 choose 3 are exactly the same thing. What about this one over here? So we are picking n being 2 in this case. So this one becomes 4 choose 2. Is that okay? So what is 4 choose 2? So 4 choose 2, we express everything in factorial and see whether this makes sense or not. 4 factorial on top, and then we have 2 factorial, and 2 factorial as the denominator because 4 minus 2 is 2. So what is that number? 4 factorial is 4 times 3 times 2 times 1, which is 24. And 2 factorial is 2 times 1 is 2. 2 times 2. So we have a denominator of 4, a numerator of 24, so we have 6. Well, that 6 turns out to be the same thing as 3 plus 3. So it works out in this case. Does that mean Pascal's identity works in general? I found one particular n and one particular k where the equality works out. Does it mean that it works out in general? No. So what do we need to do? We need to prove it, right? Okay. So when you want to prove something like this, how do you go about doing it? Now there are two things going on here. The first one is I need this to work for any n. And then the second thing is once you have chosen an n, I want it to work for every single k that is going from 1 to n minus 1. It actually works from all the way from 0 to n, but in this case, I'm only stating the theorem so that k goes from 1 to n minus 1. So how do we prove that? Yep. N is just how many things you're choosing from, and then k is k and k minus 1 is representing how many things you're choosing out of the n items. And then this representation is n choose k and n choose k minus 1, which is basically asking how many combinations can you get choosing k items out of n, how many combinations can you get choosing k minus 1 items out of n.
So in your example, the Pascal triangle, how is it related to n and k?
Okay, so let's take a look at the Pascal's triangle. And that's, nope, not this one, this guy, okay. So, cover that. Because the other one is very psychedelic. People may fall asleep or have may think of things that are not related to this class. Okay, so that's, okay. This 3 here is 3 choose 1. Okay, this 3 here is 3 choose 2. This 6 over here is 4 choose 2. That's how they're related. Okay, let me see if I can do this part here. This is for n equals to 0. Let's see, 0, 1, 2, 3. Okay, that's correct. So this is n equals 1. This is n equals 2. And this is n equals 3. This is n equals 4. Is that okay? Okay. So then you have to look at the diagonal line. Okay, so you have to look at this diagonal line here. So this entire diagonal line is representing, so all the diagonal lines are related to k's. So in this case, k equals to 0 is representing that whole diagonal line of 1s. Is that okay? This diagonal line, which is 1, 2, 3, 4, 5, is representing the case when k equals 1. Okay. I'm just using a vertical bar here to kind of link those two. This diagonal line is representing what happens when k equals 2. And then this one is representing what happens when k equals 3. And so on. Are we still doing okay so far? I can only approximate, the shape of a triangle, given this is just a text editor. Is that okay? All right. Okay. So knowing how n is controlling the rows and then k is controlling which diagonal line we are talking about, that the Pascal's triangle is basically saying when you add up these two, okay, pick any two, it will be the same, as this number here. But these two are not just any number. This 3 turns out to be, let's look up the n here. This is 3, choose 1. This 3 here is 3, choose 2. Okay? But this 6 is corresponding to 4, choose 2. Okay? So Pascal's triangle is a visual way to see how the theorem works out. It's not a proof of the theorem, it is simply a different way of looking at the theorem. Are we doing okay so far with this? Okay? All right. So switching back to the proof itself, okay, which is this one. The proof itself, this is a direct proof. A direct proof is basically just moving forward all the time. There's no trick in it. It's not a proof by contradiction, where we have to negate the theorem and then show that the negation of the theorem leads to false. It is not proof by induction, where you start with a base case and then you have an induction step. It's none of those. Okay, this one is just algebra. So we'll go ahead and take a look at how this works out. The first line is easy. The first line is just looking at n choose k minus 1, and then we express each one as factorials. Are we doing okay so far with this? Okay? Because n choose k is by definition n factorial divided by the product of k factorial and n minus k the whole thing factorial. N choose k minus 1 is n factorial divided by n minus 1 factorial, and then times n minus k minus 1 as a whole, the whole thing factorial. But that's just by definition. No surprises here. Is that okay so far? Okay. How do we move from the first to the second row? What got changed? The first part doesn't got changed at all. The second part is changed, but very, very minor way. How did I change it? I used the associative law, and instead of having the minus 1 inside something that is being subtracted, I took that out, to become a plus 1, and then I associate the n with a k, so now we have n minus k, the whole thing in parentheses, and then plus 1. Okay, the value doesn't get changed. It is still the same kind of value. It's just that the way I express it is a little bit different. Okay, no big deal, right? Okay. Moving on to the third line. Now, from the second to the third line, it is just introducing k. That's all. I'm just multiplying in the second term. I'm multiplying both the numerator and the denominator by k. The numerator is easy. N factorial times k is n factorial times k. Okay? There's no simplification here. But the denominator has some interesting simplification, because this is k minus 1 factorial already, this part here. Okay. This part here is n minus 1, k minus 1, the whole thing factorial. What happens when I multiply k to k minus 1 factorial? I get k factorial, okay? So this is going to be a very useful trick, okay? Not only in this proof, but also in the next proof, this is going to be one of the tricks. So by multiplying both the numerator by k and the denominator by k, I get to the third row. Is that okay? All right, so moving on. What about from the third row to the fourth row? What did I do? I divide both the numerator and the denominator by n minus k plus 1. Yep, okay, very good. So by dividing n minus k plus 1 from n minus k plus 1 factorial, I get n minus k factorial. Is that okay? Sort of? Okay, let me say that one more time. This time I'll point to what I say. If I divide this amount by n minus k plus 1, what do I get? I get n minus k factorial. Because I'm just still taking out the last term of that long string of multiplication. Are we still doing okay so far with the division of the denominator? Okay? But for the numerator, there's nothing I can really do to simplify it. So in order to express that I'm dividing the numerator by n minus k plus 1, I'm just going to express that, okay? So the numerator now becomes n factorial times k, the whole thing divided by n minus k plus 1 as a denominator. Are we still doing okay so far on the fourth row? Okay. What about from the fourth row to the fifth row? Okay, the second part remained exactly the same. I didn't do a single thing to it. What about the first part? What am I doing to it?
Common denominator.
Sorry?
You got a common denominator.
Yep, we got a common denominator, but I'm doing something else, over here, because I want, n factorial to also have the same denominator of n minus k plus 1, and the easiest way to do it is to multiply it by 1. That 1 being n minus k plus 1, and divided by n minus k plus 1. So it's better for me to just point to it. If you look at this part here, that's just 1. It's not changing the value of anything, but it does end up with the same denominator, so that I can now do some simplifications. It allows me to move on to the fifth step, or the sixth step in this case. Because now we have everything being common, okay? The denominator of the entire thing are now the same, so we can now say, okay, they're the same. But even the denominator of the numerator are the same as well, so we can now combine those two as well. So now we just have to add the numerator and the numerator together. So now we have n factorial times n plus 1 minus k plus n factorial k. Now there's one little trick I did here. I moved the plus 1 so it's next to n, and then move the minus k to the last part. Is that okay? All right. So simple algebra, just moving things around inside an addition. So from this step to this step, what did I do? I move n minus k plus 1 into the actual denominator of the entire thing. Okay, that's no big deal, right? I mean, you can always combine the denominator like that. And then for the numerator, what did I do to the numerator?
Cancel out the k factorial k.
I use distribution, right? I use distribution because this is n factorial. Okay. Yeah, I just use distribution. I use distribution because n factorial times n plus 1 is n plus 1 factorial. So that's why we have this one. The k, I really can't do anything about it, and that's why we end up with an minus n factorial k. The n factorial comes from here, the negative comes from here, and then the k comes from here. And then we combine that with n factorial k, which is already here in the previous step. Is that okay? So going from this particular step to the next one is really just a distribution of this term here. Are we still doing okay so far with this? Once we have this, we have these two terms canceling, and minus n factorial k plus n factorial k cancels out, so it becomes just 0. So now we are now left with n plus 1, the whole thing factorial, divided by k factorial, n minus k plus 1 factorial. And then I just did one last trick, moving the plus 1 next to n, and then moving the minus k all the way to the end, and then put parentheses around n plus 1, and I ended up with this second last row. Is that okay? And then from the second last row to the last row is just the definition of n plus 1 choose k. So this is a direct proof. In other words, I'm just deriving things from what I was given with, and then just use algebra to solve this whole thing. So I'll give you guys a moment to take a look at this. If you have any questions about this proof, let me know. The trick, the trick of this particular proof is how do we turn n factorial into n plus 1 factorial by multiplying it by n plus 1. So we are using tricks that can only be applied when we're dealing with factorial. Are we still doing okay so far with this? Do you think the other web page is proving it the same way?
Proves it different.
Yep. So that means there are different ways of proving exactly the same thing. This is my own proof. I didn't read anything. Wow, I did this. It was a challenge. I mean, I would like to be able to do it. I don't know whether the other one is easier or not. So the other proof is this one. Yeah, looks a little bit easier. It just went a different path. Okay, so let's take a look at this one and see whether it makes sense or not. From here to here is just by definition. So that's the definition of choosing. From here to here, it is just factoring out the n minus 1 factorial. And then it's cross multiplying the k and n minus k. So they're skipping a few steps here. It looks simpler because they skip more steps than I did. I spelled out the steps a little bit more verbosely compared to this one. But it still comes to the same conclusion without using proof by contradiction or in proof by induction. So, any questions about this one?
Can you explain one more time how you got from the last step, from the second to last step to the last step?
From here to here,
Yes.
that's the definition of choose, of combination.
Oh yeah.
Because n choose k is like this. So in this case, we have k,
Yeah.
but we don't have n plus 1.
Okay.
But it follows the same form as n choose k, except we have n plus 1 choose k. Okay? So we have just looked at the how of the entire proof. Low-level stuff, can be kind of detailed. There's a lot of details to it. What is it? What have we just seen at this point? In other words, what is the big deal of establishing this part here equals to this part here? What is the big deal of this? It has a name. What is the name of this thing? What is the name of this equality? Pascal's identity. Very good. So we have just proven Pascal's identity. Very good. So now we know the how, which is the low-level stuff, the algebra of actually proving it. We know the what. What it is, it's called Pascal's identity. And then the next question is why? Why do you think that is even important? Yep.
Because we can use it in this computers and programming.
How? Okay, so the how, the why part cannot be known unless you have read the next slide. Okay? Because this is what we need to prove the binomial theorem. In other words, this is a small theorem. It's a small step so that we can perform a bigger step in the next slide. Is that okay? All right. So are we ready to move on to the binomial theorem? Sort of. Okay, but before we move forward, okay, let me try to get you to understand the why of the whole thing about binomial theorem and all kinds of stuff like that. Why is that useful? What was the first context where Pascal's triangle was useful to you? We know what it looks like, right? We know how to come up with the numbers, but what is the application of Pascal's triangle? Yes?
Expanding the binomial that's under power.
Exactly. So it gives you the coefficients of all the power terms in a binomial, in something plus something to the power of something, right? Okay, very good. Okay, but why is that important to us? Since we're talking about probability, this is not a math class. We don't talk about binomials. Yep.
So you don't want to do it manually. You want to automate it or make it easier. And so you can automate it by using this identity.
Okay, but what am I automating?
Creating
The table. Okay. Well, the table is pretty easy to do. You can just use an array to do it because all you're doing is adding the items of a previous row. So you can use an array or a two-dimensional array to quite quickly do it. So you can come up with all the coefficients. But why do you think those coefficients are useful? Why, in a normal math class, how do you use a Pascal's triangle? Okay. Pretty sure you guys know the answer to this one, right? Because what you're interested in is something like this: 1 plus x to the power of n, right? And then you have to figure out, let's say it's 4, okay? Since we already have that role in the Pascal's triangle, so how many ones do we get? I mean, constant 1. We get only 1. Very good. How many x do we get? X raised to the power of 1. How many of those do we get? No.
4.
We got 4 of those. Okay, very good. How about x squared? How many x to the power of 2's do we get? 6 of those. You guys are just reading off the table, aren't you? Okay. What about x to the power of third power cubed? 4 of those. And what about x to the power of 4? 1 of those. Okay, very good. So we know how to use Pascal's triangle in the context of a binomial. Okay, which is great. But why does it turn out to be that way? Has anyone ever thought about, why Pascal's triangle turns out to be useful like that? How do we come up with 4x? Well, so what you do is you multiply out, right? It's kind of silly, right? Isn't that also one way to express 1 plus x to the power of 4? Okay, very good. How do we know that we should have 4x? Or 4 times x to the power of 1? Because you got 4, right? You have 4, 1 plus x, right? How many x can you choose? In other words, you can only choose x in some of these, then the other ones you have to choose 1, right? Because you have to choose one or the other when you're doing the product. Is that okay? Okay. So if you're looking at just x or x raised to the power of 1, I can choose x in the first 1 plus x, and then I can choose 1, 1, 1 in the other 3. Is that making any sense? Well, that's only one way to do it, but I can also choose 1 in the first 1 plus x, and then in the second 1 plus x, I choose the x, and then in the other 2, I choose the 1. Is that making any sense? I can also do it the other way, like that, right? I can also do it the last way, which is 1 times 1 times 1 times x. Okay? These are the 4 ways that I can multiply terms in each 1 plus x so that I end up with x to the power of 1. Making any sense? Okay. What about x squared? How do I know that I should have 6x squared? Because there are 6 ways to get it. Okay, very good. Okay, so which 6 ways are we talking about? I'm going to forget about the multiplication symbol because it's just taking up time. So we got x, x, 1, 1, right? x1, x1. We got x, 1, 1, x. Okay. You can see this is kind of systematic, right? Then we get 1, x, x, 1. Then we got 1, x, 1, x. And then what do we get? 1, 1, x, x, and that's it. Does it remind you of something that we have already talked about? Choosing, okay? Out of the 4, 1 plus x, how many ways can I choose 2 x's? 6. How many ways can I choose 1x? 4 choose 1 is 4. Well, that doesn't explain the 1. Yes, it does. Because the 1 is explaining how many x raised to the power of 0 do we get. In other words, out of 4 things, how many ways can we choose 0 out of those 4 things? 1 way. Okay? What about the last term? What about x to the power of 4? How many ways can we choose 4 x's out of 4? 1 plus x. Exactly 1 way. Because you have to choose x in every single one of them, so you only got 1 way to do that. That is why all of these numbers in Pascal's triangle, they are all combinations. All of these numbers are combinations. Is that okay so far? Are we relating Pascal's triangle to what you usually do, which is binomials, but also to the concept that we have talked about in this class, which is combinations, or choosing? Okay, that's boring stuff. We want to go to a casino and do something exciting, right? So we want to go, place bets on, coin tosses. Okay? So what are the chances that you can end up with, let's say we have 4 coin tosses, okay? Because we have those on the whiteboard, on projector already. So out of 4, tosses, what are the chances that we might end up with 2 heads and 2 tails? Ordering is not important. It can be head, tail, tail, head, and so on, okay? But what are the chances? Somebody is flipping a coin exactly 4 times, and I want 2 heads and 2 tails. What are the chances? You got all the numbers on the projector already, so the question is, how do you use those numbers to come up with a probability? What are the numbers telling you? Okay, so look at the row where n equals 4. So look at this row here. What are these numbers talking about? What are they talking about?
So like 4 and 16, like you add up all the numbers that you
When you add up all the numbers, they come up to 16 because there are 16 possible outcomes when you are tossing.
4 out of the 16? 4 out of the 16?
No.
8 times
2 heads and 2 tails. Which number is representing 2 heads and 2 tails? 6. Okay. So 6 divided by 16 is the probability. There are 16 possible outcomes, of which 6 are having 2 heads and 2 tails.
How do we know the 6 was that?
How do we know what?
The 6 with 2 heads, 2 tails.
Because we just worked it out.
Oh, all the x's.
Yes. So the way you look at this is you look at the polynomial no longer as a binomial, like in the math class. Instead, you look at this as, okay, let me switch this one, okay? Head or tail. Is that making any sense? So when you have heads and tails, then what is this one? One doesn't make any sense anymore. Now, when we did have 1 plus x, how did we come up with that 1 to begin with? It's 1 times 1 times 1 times 1. We did not choose a single x. We only chose ones, right? So when we convert it into head and tail, what is this representing? 4 heads, right? So head to the power of 4, because we have 4 heads. What about 4x? What is it representing in this case? 3 heads and 1 tail. Okay, so we have 3 heads and 1 tail. This one is 2 heads and 2 tails. Okay, so we got 6 of those. Okay, let me put a 4 here. So we got 6 of these because we have 2 1s and 2 x. The 1s are the heads, the x are the tails. So in this case, we have 2 heads and 2 tails. Oops, there we go. What about this guy? The 1 is implicit. The 1 is the head, but it is implicit It has got 3 eggs, which is 3 tails. So it's 1 head, 3 tails. So we have 6 of these, which is 1 head and 3 tails. And then the last one is choosing only 4 tails. Okay. Yep. There we go. So we have just transformed a binomial into head-tail. Okay? So the frequency of how you can end up with 2 heads and 2 tails becomes proportional to the probability. The total number of possibility is 2 to the power of 4, which is 16. But why is that 16? I mean, you add up these numbers, it ends up at 16, but there's another explanation. Each coin toss is independent to all of the other coin tosses, right? So how many outcomes do we have from the first trial, the first coin toss? 2, right? Okay. Is this kind of experiment with or without replacement? Once a coin lands on tail, does it go away?
With replacement.
No. So it's with replacement, right? So the second toss, the second trial out of an experiment of 4 has how many possible outcomes? 2 outcomes. The third one, 2 outcomes. The last one, 2 outcomes. So that's why we have 2 times 2 times 2 times 2, which is 16. Is that okay? But why are we multiplying but not adding? Why is it not 8, which is 2 plus 2 plus 2 plus 2? Why are we not adding? Why are we multiplying? This one, if you look at the tree, it makes sense, okay? So this is the beginning of the game before the first toss. The first toss has 2 possibilities, head, tail, okay, right? So now we have 2 possible places to begin with the second toss. That is why we are multiplying. Okay? So after we toss the coin the first time, we now have 2 separate states where each one can now have 2 possible outcomes as well. So now we have 4 possible outcomes, like that. But out of each one of these 4 possible outcomes from the first 2 trials, they generate 2 possibilities as well. That's why we are multiplying and not adding. So next time when you think about, should I be multiplying or should I be adding, think in the term of a tree. Because when you think in terms of a tree, in this case, it is really clear that we should be multiplying and not adding, because each node is generating the same number of children. So this is one particular reason why 430 is a prerequisite of this class, because if you are taking 430, you probably should be starting to talk about trees right about now. Is that about right?
It's like
Couple weeks.
a couple weeks, actually.
In a couple of weeks, or?
Yeah, in a
It'll be a
couple
couple weeks.
Okay.
We have
But
a
you-
start too. We're still in sorting.
Okay, but it is related. But you can see how a tree representation to visualize this can help you understand why we are multiplying and not adding. Okay, so that's the important part. Okay. So we are almost done with the why of why we are interested in binomial distribution. Okay, it is called a distribution because when you get to n equals to 600, okay, and you plot out the frequency of each one, what do you think it's going to look like? You can start to see a kind of a shape already even at this point. Okay, what do you think it's going to look like when we get to like 600, n equals to 600?
It's be huge.
Well, it is huge because then you end up with a total of 2 to the power of 600. But what is the shape of that thing? If I were to plot it out, what is this going to look like? It's going to be a bell curve, okay? And a bell curve is a distribution. So the more n, the larger the n, the smoother the curve, because now you're having more resolution, and at some point it's going to look like just a normal curve. Okay? Is that okay so far? And that's why it is called a distribution. It's not a normal distribution, which is continuous, but this is a discrete way to get to that shape of normal distribution. Why are we interested in this? Okay, it's a normal distribution. It's normal. Okay, fine. Why are we interested in normal? Okay, so once again, we're going to a casino. Okay? So once again, we're going to a casino, and I'll just give you, these numbers here. Okay? So we'll figure out whether it makes sense or not. Because you go to a casino and you're observing, some coin tosses. Okay? So you're observing, a particular gambling table, and they are, betting on, 5 tosses. Okay? So people have to place their bet on, out of 5 tosses, how many are going to be heads, how many are going to be tails. Okay? So you're not gonna, risk your own money. So all you did was to observe. Okay? So out of your observation, you basically observe the relative frequency of 2 heads, 3 tails, out of, let's say, I'm just throwing a number here, out of 700 experiments. In other words, each experiment consists of 5 tosses, and you observe 700 of these experiments. Okay, so out of 700 experiments, the ones that end up with 2 heads and 3 tails is approximately. I have to kind of throw a number here. I'm cheating a little bit because I'm looking at the next row, which is going to be related to what we are going to do here. So let's just say that this is about 280. Okay, so 280 of these experiments end up with 2 heads and 3 tails. Order is not important. Okay, so it can be interleaving, like tail, head, tail, head, head, tail. Can be head, head, tail, tail, tail. Can be any one of those permutations. They're all counted into this category of 2 head, 3 tails. Is that okay? So now the question is, my question to you is the coin loaded or not? Is there any funny business in that coin? How would you answer that question? This is all that I'm giving you, okay? Out of 700 experiments that you observe, you counted that there are 280 of those end up with 2 heads and 3 tails. So using Pascal's Triangle, I cheated, so can you. Out of Pascal's Triangle, how do you assess whether the coin is loaded or not? Or how do you say if the coin is not loaded, what would be the expected frequency? How do you come up with that number?
5 choose 2 or 3.
5 choose 2. Okay, so that number is important. So 5 choose 2 is an important number because out of 5 experiments, this is the expected frequency to have 2 heads and 3 tails. But it doesn't become a probability until you divide it by something, right? Until you divide it by the cardinality of omega, all the possibilities. What would that be?
700. Or
Not 700. It'll be 32, or 2 to the power of 5 in this case. Does that make any sense? So when you toss a coin 5 times in one single experiment, you have 32 possible outcomes. Out of the 32 outcomes, we have 5 choose 2 that will end up with 2 heads and 3 tails. So that's why the relative frequency, or the probability in this case, is going to be, well, we just look at the table, it's 10 divided by 32. Okay? So if the coin is fair, it is not loaded, then you should be observing about a third being 2 heads and 3 tails. So out of 700, then you say, okay, out of 700, 280 out of 700, is it close to 1/3? And the answer is, it's not close to 1/3. Okay, so we'll do some calculations here. Let me see, do I have a calculator? Nope, I do not. It's okay. We'll just go ahead and abuse Google spreadsheets. I mean, the spreadsheet is no more than a gigantic calculator. Okay, so we know that the expected probability is 10 divided by 32, which is about 31.25%. Okay, the observed frequency is 280 divided by 700, which is 0.4. Now, we are not going to get into the confidence level, like, okay, maybe just by chance that this is what we're observing. But the thing is, there's one more topic that I need to bring up, and it's a pretty easy concept to understand, so I'm going to apply that concept right now, even though I'm not officially going to go over that topic at this point. So that topic is in, where did I put it? Probably here. So that concept is in here. It's called law of large numbers. Law of large numbers is basically saying when you are doing a lot of experiments, then the expected frequency, okay, should be pretty close to what you observe. When the number of experiments is not that big, then it can be all over the place. You can kind of expect things to be all over the place. 700 is a pretty big number, okay? Which basically means if you're off by 25%, chances are the coin is loaded. Is that okay so far or not? Yep.
You said that you have to be off at 25%? You said that in order for the coin to be loaded, you have to be off at 25%?
No, I'm saying, okay, so let's go back to the numbers. So you are expecting 31.25% being 2 heads and 3 tails. That's expected, okay? If the coin is fair, this is what you should be expecting. On the other hand, what you observe, which is 280 over 700, is 40%. Okay? So when you compare 40% to 31%, it's off by more than 25%. Okay? Now, being off by 25% doesn't sound like much. If you're only doing, let's say, 10 experiments and you're off by 8% or 25%, it's no big deal, because if just by chance that you have one occurrence, it's going to throw off everything by a large amount. But when you're doing 700 experiments, the chances of just by chance it is off by 25% is going to be pretty slim. So I'm not giving you the actual probability of, okay, let's say it's just by chance. What is the probability of by chance? We just observed that it is 40% of the time is 2 heads and 3 tails. I'm not going to give you that equation, but using the large number law, you kind of know that it should be pretty close to 31.25% and not off by that much to become 40%. Are we still doing okay so far with this? Okay? Yep. All right, cool. So now we go back to the binomial theorem. So once we get all the excitement out of a casino, we go back into this class and do some boring stuff. So the binomial theorem is this. This is the binomial theorem. For every natural number n, okay, it basically says 1 plus x to the power of n is the summation of n choose I times x to the power of I, which is something that we just solved, okay? But we need to prove it now. So the next question is, how do we prove this? Okay, first of all, after we talk about all the things that we have talked about up to this point, does that seem kind of natural to you from the examples that we have already observed? In the notepad that we talked about, okay, so let's go back to the notepad. Okay, from this, does it seem like the binomial theorem is just, yeah, it seems pretty reasonable, right? But how do we prove it? So this time we're going to use a different technique of proof. We're going to use proof by induction. Okay? So proof by induction is really kind of cool because you are allowed to make some interesting assumptions in proof by induction. So in this case, I'm doing proof by induction. Proof by induction basically says, let's pick one extreme of n, and then just show that for that particular value of n, the theorem is true. Okay? Since n has to be a natural number, what would be kind of a, no pun intended, natural extreme of natural numbers? 0, yes, because it has to start with 0. So that kind of makes 0 a natural extreme end of natural numbers. Does that make sense? Okay. So now we look at the rest of the theorem and just say that, is the theorem true when n equals to 1? In other words, we focus on just this part and say, is that true when n equals to 1? What do you think? So we look at this entire thing. I just need to make sure that I highlight. Oh, excellent. So we just want to make sure that this part is true when n equals to 0. Okay? What is 1 plus x, the whole thing raised to the power of 0? 1, very good. Okay? So then you look at the summation. The summation is going from, I is an index, it goes from 0 to n, which means, if you look at this as a loop, it does not exit until I is n plus 1. Then you get out of the loop. Okay? So when you look at the summation, do we have at least one term? In other words, I goes from 0 to 0. So we have exactly one term, don't we? Okay? What does that term look like? What is the coefficient? We have n being 0, choose I, and I can only be 0. 0 choose 0 should not be defined. It's undefined. Okay, we have a problem here. Are we sure that it is undefined? Well, let's double check. Okay, so how do we check whether 0 choose 0 makes any sense or not? We plug it in to n choose k, where n is 0, k is 0 as well. Okay, so I'm going to write it out here. So this is not working. I need a place to hide all the ones that are dried up. So let's do it again, put it under here. The other one is still in here, by the way. The other dry one that I hid a little bit earlier, a few classes ago, is still in there. Okay, so n choose k is by definition what again? N factorial divided by k factorial times n minus k factorial. Okay? What if n and k are both zeros? What do we get? Then we get 0 factorial divided by 0 factorial times 0 minus 0 factorial. So you get 1, because that's 1, that's 1, that's 1 too. So the whole thing is just 1. What have we just done? This is the how. What are we dealing with?
There's one way to choose nothing to nothing.
There's one way to choose nothing out of nothing. Right, correct. Okay? But it works out too. The mathematical part works out too. But how does it relate to what we are trying to do here? This is called the base case, right? So the base case says, let's fix n to be a particular extreme of all the values that n has to work with. Let's prove the theorem is true in that particular case. Have we proven that? Okay, we have proven the theorem is true when n equals to 0. Okay, n being the n in the highlighted portion in the projector. Are we okay with that? Okay, so here comes the induction step part, which is really cool. So we'll go ahead and go to that part and just kind of focus on what does it mean when we say okay, what is the induction step? So the induction step is basically saying you are allowed to make the assumption that n works, the whole thing works up to a certain n minus 1. Okay, I can pick k minus 1. So, but basically we're saying the theorem is true for any value all the way up to n minus 1. It is true for 0, it's true for 1, it's true for 2, all the way up to n minus 1. Which is basically saying 1 plus x to the power of n minus 1 is the summation of I going from 0 to n minus 1 n minus 1 choose I times x to the power of I. Okay? So we are just taking this for granted. Okay? Which is really cool. So what we need to do now is to say, assuming this is true, can we prove the next one, which is n, is true too? This is just n, choose I, x to the power of I. In other words, the big question, what you need to link is assuming this, prove this. That is proof by proof by induction. This is called the induction step. All right. So I have it expressed here. Okay. So I have expressed it here as just exactly what we wrote on the whiteboard. I said, x plus 1 to the power of n minus 1, according to the theorem, is this thing here. Can this imply the case when we are dealing with x plus 1 to the power of n? That is the question. So this is an implication. An implication is kind of cool because it is not equivalent to. In other words, I don't need it to be going both ways. I just need to go from left to right, which is a relaxed restriction compared to going in both directions. Okay. So we'll check it out. So now we basically say, okay, so the point is we start with x plus 1 to the power of n, and we want to end up with the summation of I going from 0 to n, and then each term is n choose I times x to the power of I. Okay? So these are the individual steps. Okay? It's obviously already done, which means in your exam, you won't be required to prove this. Okay? That cannot possibly be one of the questions. Okay, so how do we prove this? How did we go from line 1 to line 2? That's a big jump, don't you think? Line 1 is easy. Okay, the left-hand side of line 1 is x plus 1 to the power of n. All I did is to pick one of those things out of the entire thing and separate it. So now it becomes x plus 1 to the power of n minus 1 times x plus 1. Is that okay? Okay, it's very simple, trick in algebra. But from the first row to the second row, the first line to the second line, what makes it possible? What did I just make use of?
The assumption of the induction.
Exactly, I just made the assumption because in a proof by induction, I am given, okay, the previous case is already assumed true. So given that x plus 1 to the power of n minus 1 is this thing, I can plug it in. I can plug that in here. Is that okay? So when you're proving by induction, somewhere in the proof, you probably have to make use of the assumption that you made earlier. Okay, because that is a key to proof by induction. So that's how I can turn this thing, which is x plus 1 to the power of n minus 1, into something that looks like the theorem that I want to prove, except this one is one step short of what I need. Are we doing okay so far? Okay, so the rest is really just algebra. The next step, going from the second row to the third row, what did I do? Distribution. Okay, so I just did a distribution so that the x is going into one side and then the 1 is going to the other side. Is that okay? All right. What about from the third row to the fourth row? What did I do? This is something that you can do when you're dealing with sigma, because you can shift the whole thing by changing the expression inside the summation. Okay? So let's see whether we can find out what happened here. So what we need to do is to compare this term to this term here. How do they relate and why are they the same? Because the other term remains exactly the same, so these two, what I just highlighted must be the same. But why are they the same? They look different, slightly different. Yeah?
So if you, in the one that's highlighted, if you were to plug in 1 into your current expression, it would be the same exact thing as
Exactly. So what you're saying is, in the original one, I goes from 0 to n minus 1, and then inside the expression, I make use of I and I plus 1 in those places. In the other one, I just change the range of I to go from 1 to n instead of from 0 to n minus 1. I still end up with the same number of items inside the sigma, right? Because from 0 to n minus 1, I have n items. From 1 to n, I also have n items. But just having the same items doesn't say a single thing, because I need to make sure the values of each thing does not change either. In the original one, I have I being the item that we're choosing out of. In the new one, I have n minus 1 being the value of how many things I'm choosing out of n minus 1. So they boil down to the same thing, because I'm adding 1 to I for each term, but I'm taking 1 away when I'm actually making use of I. Cool. What about this one over here? I raise x to the power of I plus 1 in the original one, but by shifting I to become 1 larger than the previous one, I just go like, well, forget that plus 1. I'm just using I. So they would end up being exactly the same terms. Are we doing okay so far with this transition, going from the third line to the fourth line? Sort of? Yes? You get the basic idea, but just don't see the actual mechanism, or it's cool? I'm starting to sound like Randy. Yep.
Yeah, I'm not exactly sure how you got from I plus 1 to I powered by the x.
Okay, so let's go ahead and multiply the whole thing out, okay? At least the first few terms, okay? So out of the first one, so I'm gonna highlight it. Okay, so we'll highlight this portion here. Okay. So I'll just deal with the first 4 terms, okay? So the first term is gonna be what? N minus 1, choose I equals to 0, right? So you get a 0 here, times x to the power of 1, because I is 0, right? What about the second term? N minus 1, choose 1, times x to the power of 2, okay? Plus n minus 1, choose 2, times x to the power of 3. So anyway, so you can see the pattern here. We're also always choosing from n minus 1, but what we are choosing, the number of things that we're choosing out of n minus 1 is 0, 1, 2, and then the power of x is only 1 larger than the k, or how many things we're choosing out of n minus 1. Is that okay? So let's look at the second summation term. So now we look at the second summation term and go like, okay, what are the first 4 terms of these things? Okay. We are still choosing from n minus 1 because that part does not depend on I at all, right? But the first I is a 1, right? What is I minus 1? 1 minus 1 is 0, times x to the power of what? 1, okay. Do you see it now? Yeah. Okay. So I just did a trick by changing the range of I, but in the expressions, I did something to counteract that shifting of I, where it starts and where it ends. Okay, very good. All right. So from the 4th line to the 5th line, what did I do? What did I do from here to here? This one, I think I combined a few steps, so it might look a little bit eh. Okay, so what did I do here? So one thing you might want to notice is this is a single term that seems to be plucked out of a summation. This seems to be a single term that seems to be plucked out of one of the summation of one of the sigmas, right? So the question now is, where is this being plucked out of? I mean, I got this one from somewhere. Where is it coming out of?
The nth term of the first of the 2 summations on the line above.
Okay, so this one is coming from the last term of this summation. What about this one over here? It's the first term of the second sigma. Do you see that part? The last term of this particular sigma is n minus 1 choose n minus 1 times x to the power of n, which is this one here. The first term of this sigma is when I equals to 0, so it's n minus 1 choose 0 times x to the power of 0, which is this one over here. Are we still doing okay? What about these guys? This one resembles this one a lot, right? Because it's the rest of it. So when you look at the index, this is not starting from 0 anymore, it's starting from 1. No, I take it back. This is starting from 1, but it's not ending at n anymore because I just took that n out of it. I took the last term of the first sigma into its own term, so I'm only left with 1 to n minus 1. Is that okay? What about the other one? Well, pretty much the same thing. So when you look at this term, it resembles this term a lot. But when you look at the range of I, this time it starts with 1 instead of 0 because I plucked that one term out of it. I picked that term and say, you are now on your own. You're not a part of the sigma anymore. Is that okay? So by doing that, I now have the middle term that has a sigma that is common to both of these two sigmas. So it becomes one single sigma, but with two expressions in the inside. The power to x just turns out to match up anyway, because the power to x just is x to the power of I. So in both cases, so I can just factor this out on its own. Are we still doing okay so far with this? Yes?
How do you know when doing that gets you somewhere?
Sorry, say that one more time?
How do you know when doing that gets you somewhere? Like if it progresses you through the theorem?
I cannot explain that process. That's the one part that I can't explain because it's just me exploring different things in my head, and sometimes I need a piece of paper to actually write it out and go like, okay, let's see how this is going to lead me. But I know where I need to end up with, and so I'm looking for ways to unify things and to kind of break things in a certain way.
Okay.
Yep. So I can't really explain that process because that's one part that is that's not really a part of a thinking process. It's really just in personality analysis. It's called the NE or extroverted intuition. So if you go through the personality test, that's one trait of a personality. Of course, the downside of having NE is the lack of SI, which means I lack attention to details and I tend to forget things. Okay, so we're almost there. I just need maybe 30 seconds to finish this. 30 seconds, guaranteed. How do we go from here to here? Because that's the only change between these two lines. I went from here, some summation of some kind of choosing, to something kind of like that, except n is now one larger than before. Yep.
The first term there is n plus 1 plus x to the 0 power. So is that the solution?
Yes, but the question is how do I combine this term into this term? Because that's the only difference between these two lines. Yep.
Pascal identity.
Exactly, the Pascal identity. So the previous proof is only to be used in one step in binomial theorem. But good job, you spotted it. Cool. All right, so one last thing. How do we go from here to here? That's a pretty easy one. I just expanded the sigma. I expanded the index of the sigma to include 0 and n because the terms all match out anyway. So I just need to expand the I to include 0 so that I take care of this thing that is kind of dangling on its own. And then I also expand the range of I to include n, which will also take care of this thing that is currently dangling on its own. So now we have everything included in a single sigma. Okay? So we have just gone through a lot of details, a lot of how. Okay? What is this? It's the binomial theorem. Why are we interested? because we want to find out whether a coin is loaded or not at a casino or at some other place that people are placing bet. Is that okay? Now, as a computer scientist, what are the chances that you're going to go to a casino? Exactly. Okay, that's a good answer. We're not going to go to a casino because we know the odds already, not going into the casino. But what you do have to deal with is transmissions of zeros and ones. Okay? Right? And do you think transmissions are always 100% correct? To computer science people, the answer is yes. But then when you start to talk to an electrical engineer, the engineer will say, no, hell no. Okay? Bad things go on, okay? You're trying to use a Wi-Fi, and guess what? The neighbor starts to use the microwave. So now your 0 becomes a 1, and your 1 becomes a 0. So this stuff starts to become useful. What are the chances that your 1 gets transmitted in as a 0? Don't you think that might be slightly important when you're in the middle of a game? Yeah? Yeah?
Download these files.
Alrighty, so we're almost done with all this stuff. So on next Tuesday, I'll wrap this up, making sure that everybody has a big picture of how these things are useful, okay? How each one relates to the other one, and then we'll move on to yet another topic, okay? All right, have a nice weekend. I'll see you guys on Tuesday.